So in the previous chapter, the example we just did was the probability of rabies, rabies, no rabies. We said 0.2 times 0.2 times 0.8. Why was that so simple? Well, because I gave you the exact sequence. Rabies, rabies, no rabies. What if instead I just had said, out of 3 dogs, 2 have rabies? Well, that's not such a simple question anymore, because I can't just go 0.2, 0.2, 0.8. I now have to consider, well, there's different sequences. Well, that could give me one of the next 3 dogs having rabies. Maybe it's the first dog, maybe it's the second dog, maybe it's the third dog. So let's look at the probability 4 out of next 10. I'm doing these just because it's the one I wrote, not 1 out of 3. Has rabies. I can't just say, okay, rabies, 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 and then 6 non-rabies, non-rabies times 6, because that's just one of the potential sequences. Instead, I have to use the binomial distribution. So the binomial is just an extension of the multiplication rule. It's obvious how I found this through multiplication rule. The binomial is multiplication rule when I have many sequences to consider. So notice that if all 10 dogs, if I'm looking for the probability that all 10 have rabies, well, that's not binomial anymore, because if they all have rabies, there's only one possible sequence. There's no way for me to rearrange this for it to look any different. They all have rabies. So it's just multiplication. The same is true if I say none out of the 10 dogs, 0 of them have rabies. Then it's just this only one possible sequence. They all do not have rabies. It's the stuff in between the extremes, like 4, where we have to use binomial. Binomial formula is n choose k times p to the k times 1 minus p to the n minus k. So the first thing we want to do is just identify these 3 letters, n, p, and k. N is the number of trials. In this case,
10.
That'd be 10, because I'm looking at the next 10 dogs. Each one of them is a trial. It'll either have or not have rabies. P is the probability of success. Again, we don't use these words literally. In this case, success would be having rabies. What's the probability of rabies? 0.2. Probability of success. And K is the number of successes. In this case, it's 4. K is just what the question is asking me. It could be anything between 0 and 10. The 0.2 is given. It's the probability of rabies for any of those 10 dogs. It's 20%. Yes?
Sorry, this might not even matter, but I saw some other binomial formulas. They didn't use K, they used something else.
Yeah, they use X. So that depends on the book. Some, instead of K, they call it X. Then we have X as the number of successes. It doesn't actually matter what letter you use, right? I used to use X, and then I made lectures, or I got lecture slides from someone else that used K, so now I use K. It doesn't make a difference. So now that we have all these for our problem, we just plug it in. N choose K becomes 10 choose 4. Times P to the K is 0.2 to the 4th. Notice this is just multiplication. 4 rabid dogs, 20% chance they have, each dog has rabies. 0.2 to the 4th is my probability that 4 of the dogs have rabies. Again, multiplication rule, I have 80% chance a dog does not have rabies. That's 1 minus P. How many dogs don't have rabies if 4 out of 10 do? 6 out of 10. Normally we find it just n minus k, 10 minus 4. This is simple enough to put in your calculator. This, though, we need to actually find what it equals.
Factorials.
So remember that n choose k equals n factorial over k factorial over n minus k factorial, which looks nasty, but once you plug it in, it's not so bad. This would be 10 factorial over 4 factorial over n minus k is 10 minus 4 is 6 factorial. The things in your denominator are always going to be the same as the two powers in your binomial. They're the same thing, n and n minus k. 10 factorial is 10 times 9 times 8 times 7, all the way down to times 1. Four factorial is 4 times 3 times 2 times 1. Times 6 factorial in the denominator, that's 6 times 5 times 4 times 3 times 2 times 1. You're always going to get a lot of canceling out. This whole 6 times 5 all the way down to times 1 cancels with the 6 factorial we had down here. Now we have 10 times 9 times 8 times 7 over 4 times 3 times 2 times 1. You could start cross-canceling, like I can cancel out this 9 with this 3. That leaves me with a 3 on top. If you don't remember all that stuff from algebra, just go ahead and put it in your calculator the way it is. Yes. Okay. So what that comes out to is 210 once I put it in the calculator. That means there are 210 different sequences where I have 4 rabid dogs and 6 non-rabid dogs. Once I know what that equals, I can just erase it and plug in the actual number. Now it's very simple in your calculator. 210 times 0.2 to the 4th times 0.8 to the 6th gives me 0.088. So, how many dogs? So this binomial, it's actually very similar to what we do in chapter 7, actually. Think about what I'm doing here. I'm telling you that 20% of dogs have rabies. In a sample of 10, I would therefore expect 20% of them, meaning 2 of them, to have rabies. I'm looking for the probability that I actually get 40% of them having rabies. This sounds a lot like chapter 7, doesn't it, when I phrase it that way? And it is. It's actually the same thing. The only difference is chapter 7, our sample sizes are big. So when we use that central limit theorem, we're actually just approximating the binomial. If I tried to do binomial with really large samples, like 1,200 people, the way we do in chapter 7, your computer will explode when you try and do 1,200, choose 800, or whatever it is you're computing. The central limit theorem, and we don't talk about this fact much in the class, it's really just a way to approximate this sort of thing. Everything's connected. Well, yes.
Did you get factorial 6 from the exponent?
Sorry? They are the same thing. That's n minus k. In my factorial definition, I have n minus k. So it's always going to be the same. My other exponent is k, which is also in my denominator. K, n minus k, k, n minus k. That's why these will always be the same things. Yes?
Can you phrase the answer again?
For the binomial, I say there's 8.8% chance that 4 of the next 10 dogs have rabies. Notice the binomial gives me the probability of exactly 4. It's not 4 or less, it's not 4 or more. It's exactly 4, not 3, not 5. Questions there? So you're going to use the binomial when you have a k out of n situation.
So on a test, you would ask like 3 questions out of one of these, right? And like say, what is the answer?
No, for the binomial, I mean, it'd be really tough to split into multiple parts. So the binomial will be one question.
And the answer would be 8.1.
0.088.
0.08.
Yeah. Questions there? All right, in chapter 6, we learned 2 distributions. The binomial was called our discrete distribution. Discrete meaning that k can only be integer values, 0, 1, 2, 3, 4, etc. We also learned a continuous distribution, which we had already learned, the normal distribution. So how do you know a problem is a normal distribution? It should be very obvious. I have to tell you. For you to compute a probability with the normal, you have to know that the data is normal. I have to give you the parameters of the normal. That's mean and standard deviation. So I'll have to give you a mean, give you a standard deviation, and say, assume the data is approximately normally distributed. So let's go back to my Q scores, which I like because these are actual numbers. I'm not making them up, and they're easy to work with. So IQ scores have a mean of 100, a standard deviation of 15, and I'm telling you to assume that they are approximately normally distributed, which they are in reality. This is when you use the z-score, when you're dealing with a normal distribution. So what's the probability that an IQ is greater than 110? Yes.
Sorry, quick question. I just want to confirm, is discrete and normal distribution the same?
No. The normal distribution is an example of a continuous distribution. Our discrete distribution is the binomial. So in the binomial, k has to be an integer, 0, 1, 2, 3, 4, etc. Here, this IQ, I could ask you 117.32, and that would still be fine, because I can take decimals here. We normally see this in our z-scores. We don't just have z-scores of 1, 2, 3, 4, 5. They can be decimals too. That's continuous. So what's my first step here?
Find the z-score.
Find the z-score. My z-score formula is the observed x minus the mean divided by the standard deviation. So for this value, I'd have 110 minus 100 divided by 15. 10 over 15 is 0.67. So I've converted this to the probability that z is greater than 0.67. It's a greater than, so I have to use the complement rule. Remember, our z table is only written in terms of less thans. So anytime we have a greater than, we have to rewrite the question as 1 minus the probability that z is less than that value. Now we have something we can work with. I have 1 minus, so what is the probability that z is less than 0.67? Prove to me you know how to read this table. You may not have the table, so let me just blurt it in. 0.7486. It's a good time to say that on the exam, the table will be stapled to the exam. You don't need to bring your own.
Why is it the 1 minus again?
We have to do the 1 minus because the original question asked me for z greater than. But the table's only written in less thans. So we take advantage of the fact that less than is the complement of greater than. So I'm really just applying the complement rule here. In other words, if the whole distribution, if this is 100% of the area, and I want this area here, well, the table doesn't give me this, but it does give me this. So I do 100% minus this, what's left over? The thing I actually wanted. What if I give you a probability that looks like so using the same mean and standard deviation, probability that an IQ is between 100 and 120. Much like the table is not written in greater thans, it's not written in between. So we have to convert this to a special form. if I'm looking for the area between two values, we'll just call them A and B. Here's A, here's B. Same here, A, B. I'm looking for the area between A and B. The table doesn't give me that, but if I take the area to the left of B, and then I subtract from that the area to the left of A, what am I left with? The area between A and B. So we want to use that logic here. The first thing we want to do still is convert to z-scores. Probability that z is between these two values. I need a new piece of chalk here. So I'm going to convert to z-scores. What's the z-score for the value of 100? My mean is 100. What's always the z-score of the mean itself?
0.
0. Z-score is how many standard deviations from the mean a value is. The mean is never away from itself. 0. 120, you might need a calculator. I have z equals 120 minus 100 divided by 15. That gives me 20 over 15, which is 1.33. So now I have the probability that z is between 0 and 1.33. And now is where I want to follow what we talked about over there. I want to rewrite this as the probability that z is less than. So this will be the top picture that I'm doing now. Whatever b is, the larger of my two z-scores, 1.33, minus the probability that z is less than, so that would be this picture here. The smaller of my z-scores, 0. So what's the area below 1.33? I go to row 1.3, column 0.03. I get 0.9082. Minus the probability that z is less than 0. Do I need a table for that? What's the probability z is less than 0? 0 is right in the middle of the distribution, right? It is the mean. Just a half. So I get about a 41% chance that an IQ is between those two
Oh
values.
yeah, you get 0.5.
0.5, now I could go to the table and look up the z-score of 0. I'm just saying it's kind of obvious.
Oh, it is 0.5.
If 0 is obviously right in the middle,
So it's half.
so half the distribution's below 0, half of it's above
Yeah.
0. Questions there?
And this is considered what kind of problem?
This would be your standard normal distribution type problem.
And then where did you get 1.33?
That's the z-score for an IQ of 120. You always want to start by converting everything to z-score
Okay, that's right.
when you're told that it's a normal distribution.
That would be the final answer.
0.4082. Yes. The question would be, what's the probability in IQs between 100 and 120? Yes. 40.82%. So in both these questions, I gave you an IQ, and you had to convert it to a z-score to find the probability. What if instead I had given you a probability and asked you what IQ corresponds to that? We call it a percentile. A percentile is what percent of people your IQ is higher than, if we're talking IQ percentile. So what is the IQ at the 55th percentile?
Are we still in chapter 6?
Yes. So I tell you someone at the 55th percentile, meaning they're smarter than 55% of people. What is that IQ? It's kind of the same thing, but in reverse. I want to find the z-score that is the cutoff point. So if I look at the distribution, there's some z-score here where to the left I have 55% of the distribution, and to the right I have 45%. This is drawn terribly off scale. So I'm looking for that z-score there. Is it going to be positive or negative?
Negative? No.
If 55% is to the left of it and 45% is to the right of it, then is it to the left or to the right of center? It's to the right of center, so it'll be a positive z-score. How do I actually find what it is? I go to 55% on the z table, or I go to 0.55, or as close as I can get to it from the table, and I see that it's on row 0.1 and column 0.03. So that z-score is 0.13. The IQ at the 55th percentile is 0.13 standard deviations above the mean. My z-score formula is this. I solve for x, which is my goal here. I end up with x equals mu plus z sigma, z times sigma. So now I plug in what I have. I have a mean of 100, that's given. The z-score of 0.13 times my standard deviation of 15. This, I actually don't have what it comes out to, but it's 100 plus 0.13 times 15. Yes.
So anytime we look at a normal distribution and it's below 50, that means it will be negative z, right?
If the percentile is below 50, yes.
It's always negative.
And if it's above 50, it'll always be positive. And if it's exactly 50, it'll be 0, the z-score. Though that fact alone won't help much. You still need to know what the z-score is.
Right.
What is x equals m plus z times
If I take my z-score formula, so right here I know everything except x. I know z is 0.13. I know mean is 100, that was given. I know the standard deviation is 15. I want to solve for x.
Yeah.
This here is just a solution for x.
I see.
Anything else there?
Where'd you get 0.13?
This, the 0.13, that's the z-score. That came from the table. I went to the table and I looked up the 55th percentile. Or I went to 0.5500, or as close as I could get to it. And that was on row 0.1, column 0.03. So that z-score is 0.13. Questions there? All right, then let's look at chapter 7. So in chapter 7, the biggest difference is now I'm talking sampling distribution. What I just said now, I gave you the IQ, that gave you the mean and standard deviation of IQs. That was a population distribution. Now let's say I'm not talking about individuals anymore, the probability that an individual's IQ is greater than 120 or whatever. Now I'm talking about an average from a whole group. And the statistics that we work with in this class are the sample proportion, p hat. So if I take a whole group of 30 people, I compute a sample proportion there. I ask them, who are you voting for in the next election? 51% say Hillary. That's p hat. Then I take another sample. I get another sample proportion. The distribution we're talking about in chapter 7 is not the distribution of the individuals, it's the distribution of these sample statistics. If I get 1 million p hats from 1 million different samples, each of size 30, I could create a histogram of that, and that's the sampling distribution. The central limit theorem tells me that, conveniently, that histogram of all the 1 million p hats from my 1 million samples will have this normal shape. So it actually means I don't need to take 1 million samples and get 1 million p hats, because I already know, mathematically, what the distribution will look like. The result, for you guys, what this means, is that we use the same methods to find probabilities for p hat that we do when we know that the distribution itself was normal in chapter 6. So in chapter 6, I had to tell you IQ scores are approximately normally distributed. In chapter 7, I don't need to say that. the central limit theorem guarantees that they will be normally distributed. How do you know then that we're talking sampling distribution, which is guaranteed to be normally distributed? Whenever we're talking a sample statistic. So the consequence of the central limit theorem was that my new z-score is p hat minus p divided by standard deviation, which had the formula square root of p times 1 minus p over n. But because the central limit theorem says that p hat is distributed normally, once I have that, it's just like chapter 6. So let's look at an example here. Let's say I took a poll of 50 people and I asked them, do you prefer to read your news on the internet or in a printed newspaper? And let's say that 60% said internet. So let me write the question. Out of 50 people, so you need to be told, sorry, I should have started here. Assume 60% of all people prefer the internet. So that's P, my population proportion. Out of all people, 60% prefer to read their news online. Then I take a sample of 50 people. Out of 50 people, what is the probability (64% or more prefer internet? So how do you know this is sampling distribution? Well, I have a sample of 50 people. And I'm talking about out of that whole sample, the statistic, p hat, what's the probability that that is greater than 64%? So in any given sample, I expect 60% of the population prefers the internet. I'm computing the probability I get something unexpected or greater. Just by looking at this picture, is this probability going to be more or less than 50%?
Or
Less, no less.
Hmm?
It's got to be, if from 60% on up is 50%, because it's the midpoint, then 64 on up is going to be something less than that, meaning it'll be less than 50%. Of course, we want to find what it actually is, so we start with our z-score. We have p hat of 0.64 minus p of 0.60 divided by standard deviation of square root p is 0.6 times 1 minus p is 0.4 divided by the sample size 50. We get a z-score of 0.58. Once I have that z-score, which is now the product of this being normal due to central limit theorem, so we have this different z-score for proportions, a lot of little details, but once we get to the z-score, it's just how we've always understood the z-score. This is telling me that this point, the 64%, is 0.58 standard deviations away from the 60%. So what is that probability? That z is greater than 0.58. Just like chapter 6, it's a greater than, so I have to use the complement rule. 1 minus the probability that z is less than 0.58 gives me 1 minus, so I go to row 0.5, column 0.08, I get 0.7190. For 0.281. So as expected, it's something less than half because it's something different from what, something above the average, right? So any sample, I expect 60% of people prefer the internet. But there's still some probability that I get an exceptional sample where 64% or more prefer the internet. There's roughly a 28% chance of that occurring. Questions there? We also used the central limit theorem, or the fact that the distribution of p hat is that bell curve, the normal, to put a margin of error on our estimates. So let's say, so our formula for confidence intervals, I'll put it up here now, is p hat plus minus my margin of error. My margin of error is composed of z critical.
Is this a new problem?
Yeah, it's still chapter 7. We're using central limit theorem, but now we're talking about confidence intervals. Did you have a question on the last one? My margin of error is z critical times the standard error. The whole point of the confidence interval is to estimate p, meaning I don't know p, so I can't find the actual standard deviation. So we go with the next best thing, the standard error, which is the same formula but with p hat instead of p. That's my formula for confidence interval. How will I know a problem is a confidence interval problem? So this one's really easy. I have to specifically ask you, give me the something % confidence interval. So there will be no confusion as to when to apply this formula. So let's say in a sample of 100 people, %, pass the bar exam on their first try.
Bless you.
Bless you. Give a 60% confidence interval. For the population proportion, so this is a mouthful, the population proportion of people who pass the bar exam on the first try. Okay. This is why I use lecture slides during lecture. I hate writing that much. So I don't know, I have no estimate even of the true proportion of all people who take the bar who pass it on their first try. So to estimate that quantity, I take a sample of 100 people. 15% of them, meaning just 15 people, had passed it on their first try. So that is my estimate of the percent of people in the whole population that passed it on their first try, 15%. But because that came from a random sample, I know it's not exactly correct. So I want to put some margin of error around that estimate. So I have 0.15 plus minus my margin of error. The question is, what is z critical? So I have given you z critical for the 3 most common confidence levels. This is confidence level. This is z critical. For 90, it was 1.645. For 95, it was 1.96. For 99, it was 2.575. Put these on your cheat sheet. I think in lecture we also found that 80 was 1.28. This one asks for 60. So let's practice how do we find it. And you'll use the same method for any confidence level, even 90 or 95.
I'm sorry, when do you use this confidence level?
I'm sorry?
When do you use this confidence level?
Anytime you're asked for a confidence interval.
Okay,
That's how you determine z critical. It's based off the confidence level.
I see.
So this question asked me for a 60% confidence interval. So I need to find what the z critical is for 60 because I don't know it already. The way I find that is a confidence interval. I'm setting p hat to the center of the normal distribution, and then I want to find the boundary points of this middle 60% of the data. This is what a 60% confidence interval is. So to do that, my z critical is this z score right here. So I need to use the z table to find what this z is. How much area is to the left of this z score?
40.
On the right track. Outside of the middle 60, I have a total of what? 40. By symmetry, half that 40 is here and the other half is here.
20, 20.
So that's 20 and 20. So now how much is to the left of here? 80. This whole shaded area is 0.8. So now I'm going to go to my z table and I'm going to look for 0.8 or as close as I can get to it. Not at the z-score column, but in the interior of the table. As close as I can get to 0.8 is 0.7995, so really close. That is on row 0.8 and column 0.04. So that z-score is 0.84. And then that's what I'm going to plug into my confidence interval formula for z critical. 0.84 times, this one's much simpler. I just plug in the given p hat, so I have square root 0.15 times 1 minus p hat, 1 minus 0.15 is 0.85, divided by my sample size n, 100 people.
Mr. Baltar, you got 0.84 from the z table,
Yes.
so that's just closest to 0.8, right?
Yeah, I went in the table here, I found 0.7995, the closest I could to 0.8. That was on row 0.8
I see.
and column 0.04. So that's where that z-score came from. So this is it. Then you put that in your calculator. If I do the whole margin of error in my calculator, I get 0.03. So my interval, let me write it over here now. 0.15 with a margin of error of 0.03. That's what we got over there. We typically take it a step further. 0.15 minus 0.03, that's 12%. 15 plus 3, that's 18%. So this means that my p hat of 15% for the proportion of people who pass the bar on their first try leaves me 60% confident that the true value of people who pass the bar on their first attempt is between 12 and 18%. Or in other words, 15% with a margin of error of 3%. Yes, I'm 60% confident that the true proportion P of people who pass the bar on the first attempt is between 12 and 18%. In other words, between 12 and 18% of people pass the bar on their first try. And I'm 60% confident that that's true.
When it is with the bracket off.
Yeah, it's exactly. It's my margin of error. It's the thing after the plus minus.
Z-score for the 60 was 0.84.
0.84. No matter what I ask you though, you're going to find it the same way we did right here. Any questions on chapter 7 before we go to chapter 8?
So after computing the points array with the square root, you get 0.43.
After I do 0.84 times this whole thing, yes, I get 0.03, yes. That's my margin of error.
Do we have to round numbers in the beginning or at the end? If we ever get like 0.889 or something.
For what?
For any of the numbers.
In general, round to 2 decimals. Z-scores you have to because the table only goes to 2 decimals for the Z-score itself. The only time I recommend rounding to 3 decimals is when you're looking at this square root p or p hat times 1 minus p over n. The standard deviation or standard error, in other words.
The table that you give us has
Yes, the table I will give you is the same one I passed out in class. This table here. Any other questions from chapter 7? All right, let's look at chapter 8. So you may have thought because it's the last day that I forgot practice problems, but I did not. I just saved them for the chapter 8 part. So on the board, I'm going to write the steps to a hypothesis test. And like we usually do with practice problems, I'll give you 10 minutes to work on these, and then we'll go over them. Would you help me with passing
Yeah,
this
of
out?
course.